So today we're going to turn our attention to two new functions. Specifically, we're going to look at the piecewise function as well as the greatest integer function. So far, we have seen many graphs that are expressed as single equations and are continuous over a domain of real numbers. We have also seen the discrete functions, which are comprised of separate, unconnected points. There are also graphs that are defined by different equations over different sections of the graphs. These graphs may be continuous or they may contain breaks, which are called points of discontinuity. We've already looked at jumps and holes. Because these graphs tend to look like pieces glued together to form a graph, they're commonly referred to as piecewise functions. A piecewise function is a function defined by at least two functions or pieces, each of which applies to a different part of the domain. Piecewise defined functions can take a variety of forms. Their pieces may be linear, or they may be a combination of different types of functional forms, including constant functions, linear functions, quadratics, cubic, square root, cube root, and exponential functions. Due to this diversity, there is no parent function for a piecewise function. The examples that we'll look at below will contain some linear, some quadratic, and some constant pieces. So exactly how do we graph a piecewise function? There's really two suggested ways to go about doing this. Option one is to create a table for each of the function's pieces to help us graph based off the given restrictions. Option two is to use what I call the eraser method. This involves graphing both functions entirely and then erasing the part of the function where the domain is not included. For this particular video, I'm going to use option one. So let's go ahead and look at this first example of a piecewise function. Here we can see we have f of x equals 2x plus 3, where x has to be less than or equal to 1, as well as f of x equals negative x plus 4, where x has to be greater than 1. I'm going to go ahead and set up two separate tables for each of these two functions. Starting with 2x plus 3, I know that x has to be less than or equal to 1. So I'm going to start with x being 1, and then I know I need to pick values for x that are smaller than 1. So 0, negative 1, negative 2. And let's go ahead and plug 1 in. So 2 times 1 is 2 plus 3 is 5. 2 times 0 is 0 plus 3 is 3. 2 times negative 1 is negative 2 plus 3 is 1. Negative 2 times 2 is negative 4 plus 3 is negative 1. Now I'm going to do that same process, but with the second function of this piecewise function, negative x plus 4, where x has to be greater than 1. So I'm going to start with 1. Negative 1 plus 4 is 3. I'm going to then go bigger since I need values for x that are greater than 1. So 2. Negative 2 plus 4 is 2. 3. Negative 3 plus 4 is 1. 4. Negative 4 plus 4 is 0. And now we can go ahead and plot these points. So we got 1, 5, 0, 3, negative 1, 1, negative 2, negative 1. And if you can see, again, our inequality says our domain restriction needs to be for all values for x less than or equal to 1. So starting at x equals 1, I'm going to include all points to the left, because that represents the value smaller than or equal to 1. And then for my second function, negative x plus 4, x has to be greater than 1. We got x is 1 when y is 3. And that is going to be an open circle. That point is not included, because if you look at the inequality again, we got x is greater than 1. So we got 1, 3, 2, 2, 3, 1, 4, 0. And since I want the domain to only include values of x greater than 1, I'm going to draw in my points going towards the right, since that's where x is greater than 1. And that's a piecewise function. Let's go ahead and turn our attention to our second type of functions for today. That's called the greatest integer function, which is also known as a step function. And what's unique about a greatest integer or step function is that it's actually a piecewise function. It's just containing all constant pieces. Remember, constant means that it's not increasing or decreasing. The y values are constantly staying the same. The constant pieces are observed across the adjacent intervals of the function as they change value from one interval to the next. A greatest integer function is discontinuous. So again, that means you cannot draw a step function without actually removing your pencil from your paper. The greatest integer function, by definition, will return the largest integer less than or equal to x for all real numbers x. In essence, the greatest integer function rounds down a real number to the nearest integer. Let's take a look at a few examples of what I'm talking about here. So the greatest integer, 2, would be rounded down to 2. The greatest integer, let's say of 1.5, gets rounded down to 1. The greatest integer of negative 3.1 gets rounded down to negative 4, and negative 6.9, the greatest integer rounds down to negative 7. So you can see by these 4 examples that the greatest integer function simply rounds down any real number to the nearest integer. So how do we graph a greatest integer function? To do this, we're going to again make a table and choose some real numbers that will return the largest integer less than or equal to that particular number. So to get started with my table, let's pick some basic real numbers, starting with 0. If I was to ask you take 0 and round it down to the nearest integer, well, that would round down to 0. If I pick 0.1, well, that would round down to 0. 0.5 would round down to 0. 0.9 would round down to 0. 0.99 would round down to 0. So if I chose 1, 1 would round down to 1. So anything starting at 0 rounds down to 0, all the way up to 1, but 1 is not included, because when we hit 1, we get a y value of 1, so 1, 1. And then I could repeat this process again. 1.1 rounds down to 1, 1.5 rounds down to 1, 1.7 rounds down to 1, 1.99 rounds down to 1, and this process would literally continue. So for any value of 1, I get 1, and anything less than 2 rounds down to 1. Any value less than 3 rounds down to 3. Any value less than 4 rounds down to 4. Any value less than 5 rounds down to 5. Any value less than 6 rounds down to 6. And I could keep doing this. Any value less than 0 rounds down to negative 1. Any value less than negative 1 rounds down to negative 2. And you can see here that I'm starting to form a graph that looks like a bunch of steps. Hence, the greatest integer function is known as a step function. Let's go ahead and do some practice involving both piecewise and greatest integer functions. In example problem number 1, we have f of x equals a quadratic, where x has to be greater than or equal to 3. We have f of x equaling a linear, which x has to be greater than 0 and less than 3. And we have f of x equaling an absolute value, where x has to be less than or equal to 0. So let's go ahead and start by plugging in values for our first table, which will be for our quadratic. So we have x has to be greater than or equal to 3, so I want 3 and then values bigger. So let's start with 3, 4, 5, and 6. Let's plug in 3. 3 minus 5 is negative 2, squared is 4, times a negative is negative 4, plus 8 is 4. Plug in 4, 4 minus 5 is negative 1, squared is 1, times it by a negative is negative 1, plus 8 is 7. Plug in 5, 5 minus 5 is 0, squared is 0, times it by a negative is still 0, plus 8 is 8. Plug in 6, 6 minus 5 is 1, squared is 1, times it by a negative is negative 1, plus 8 is 7. So we have 3, 4, and that 3 is included based off this given domain restriction where x is greater than or equal to 3, 4, 7, 5, 8, 6, 7. And we're starting at x is greater than or equal to 3, and it keeps going on forever. All right, let's look at our linear function. where x has to be between 0 and 3. So I'm going to start at 0, 1, 2, finish at 3. So 3 times 0 is 0, minus 8 is negative 8. 3 times 1 is 3, minus 8 is negative 5. 3 times 2 is 6, minus 8 is negative 2. 3 times 3 is 9, minus 8 is 1. And again, let's look at our domain restriction. So x has to be greater than 0, which means 0, negative 8 is not included. So we'll make that an open circle. 1, negative 5. 2, negative 2. 3, 1. And I am only graphing those values between 0 and 3. So we only get part of that linear graph again. And then finally, our third function of this piecewise is an absolute value. And we want values that are less than or equal to 0. So we're going to go with 0, negative 1, negative 2, negative 3. Those are all values less than or equal to 0. Plug in 0. 0 plus 6 is 6. Absolute value of 6 is still 6. Minus 7 is negative 1. Negative 1 plus 6 is 5. 5 minus 7 is negative 2. Negative 2 plus 6 is 4. Absolute value of 4 is still 4. Minus 7 is negative 3. Negative 3 plus 6 is 3. Minus 7 is negative 4. So we have 0, negative 1. And that point is included because of the equal to symbol. Negative 1, negative 2. Negative 2, negative 3. And negative 3, negative 4. Now, I know that 0 was included. And so right now it looks like I'm just drawing a line. However, this is an absolute value function. And you should see based off our transformations, we're going to be shifting to the left 6 and down 7. So that is my vertex. So I'm going to go to the left 6, 1, 2, 3, 4, 5, 6, down 7. So I know that this is going to be a V-shaped graph, hitting my vertex and then bouncing back up and going on forever in that direction. Now for this last part, they're asking us to look at each of these different functions evaluated for certain x values. So f of 3, they're asking us which function would I plug 3 in for x? And to figure that out, you got to look at these 3 restrictions. The only one in which the function includes 3 is this first one. So I'm going to plug in 3 for x into equation 1, the quadratic. So we have 3 minus 5 is negative 2. Squared is 4, times it by a negative is negative 4, plus 8 is 4. Now the only one that satisfies where x could be 13 is again equation 1, so we'll plug it into the quadratic function. 13 minus 5 is 8, squared is 64, times it by a negative is negative 64, plus 8 is negative 56. The only function that I could plug x to be 1 in based off those domain restrictions is equation number 2, which is my linear function. So 3 times 1 is 3, minus 8 is negative 5. The only function I could plug 0 into, in which 0 is included in my domain, is equation number 3, the absolute value. So 0 plus 6 is 6. The absolute value of 6 is still 6. Minus 7 is negative 1. And the only function I could plug x to be negative 3 into is, again, equation number 3, since x could be less than or equal to 0. So negative 3 plus 6 is 3. Absolute value of 3 is 3. Minus 7 is negative 4. Now in example number 2, it says accurately graph the step function. It says f of x equals 2 times the greatest integer of x. Well, if you recall back, the greatest integer had increments of 1. This 2 in front tells me that I have a vertical stretch by a factor of 2. So what does that mean? That means I'm taking my first step and I'm going to stretch it by a factor of 2. So the next spot won't be at 1. I'm going to go up to 2. And every value less than 2 will round down to 2. Then I'll go up to 4. Every value less than 4 will round down to 4. Then I'll go up to 6. Every value less than 6 will round down to 6. And then from my origin, I can go down 2. And every value less than 0 will round down to -1. And I could repeat this process again.